So like I said, I actually think it's interesting. I think ER modeling, it's easy to understand the concepts. It's hard to apply them. Normalization is sometimes a little harder to understand the concepts because it's more of a mathematical approach to design, but it's easier to apply because there's fixed rules that are very explicit. There's a good, well-defined algorithm. So, um, like I say, normalization, I would actually say it's a bottom-up design technique and it's a more mathematical technique for decomposing relations into smaller relations. Basically, doing it so that you're grouping logically related attributes together. And essentially what normalization is trying to get at is the same thing that entity relationship modeling is seeking to get at, which is that when you're done with normalization, typically each relation will represent either an entity, a single entity. You won't have any relation representing two entities when you're done. Each relation will represent only one entity, or the relation will be modeling a relationship, or it will be modeling a multi-valued attribute, which is the same set of relations you would come to from ER design, just you'd come at it from a top-down perspective. Okay, so with normalization, it's true for ER modeling too, what you're trying to do is minimize the amount of redundant data in the database. And by minimizing the amount of redundant data, you're going to minimize the chances for having inconsistencies in the database. What you're essentially trying to do is limit the redundancy to foreign keys, meaning foreign keys, which are what you're using to perform joins, have to be redundant. Okay, so if you have branch B005 and you have a staff member belonging to branch B005, there's really no way to get away from the fact that B005 is duplicated for each staff member that works at that branch. You can't get away from duplication in foreign keys. But what you're trying to do is basically isolate the redundancy to foreign keys if possible. And this is a diagram from the book, but basically it's trying to show where normalization fits in the scheme of things. So on the left-hand side, it's where it's your information sources. Like it's interviews with users, it is reports, forms, invoices, contracts, leases, where you get your data that you're going to be using to create your relations. And then this top box says that you can either use a top-down approach such as ER modeling and then verify on the right. I know it's hard to read. What it's saying is you use normalization to check your relations that you derive using ER modeling. So basically, once you've done the top-down approach, you then check that everything is okay by using the normalization approach. And then the second approach, which they call approach 1, is to simply go from the bottom up using normalization. It's just as I said, most experts don't think that way. They start from the big picture. They see the forest and break it down into trees rather than seeing the trees and trying to move up to the forest. Okay, so with ER modeling, you didn't really see the issue with that you can get with inconsistent data. So it really comes up when you're doing normalization. Let's say that your first crack, that you kind of take a first crack at things. And one natural way to organize things is with directories, like we're used to, like the student directory or the faculty directory or a phone book. And so the staff branch relation is really like a directory. For each staff member, it's showing information about that staff member, their name, their position, their salary, the branch they work at, the branch address. So your first crack at doing design, maybe even you do this from the ER standpoint, you think, well, it's a directory of staff. But the problem is there's some data redundancy here. Can anyone give me an example of some redundant data that is in this, in here? Branch address. Yep. So everywhere you see B5, you better be seeing 22 Deer Road. Okay, if you don't, that's a data inconsistency because unless we're in quantum physics, you can't really have the branch existing at multiple locations at once. Okay, same thing when you see branch B003, it better be always at 163 Main Street, Glasgow. So that is a redundant piece of information. Other redundant pieces of information might be harder to pick out because they may or may not exist. Notice that assistant 9,000, 9,000, so you might start to think maybe all assistants make 9,000, except this one makes 12,000. So you'd want to verify, do all assistants make the same amount of money, or is it really okay for them to make different amounts of money? Or it might be that all assistants at the same branch make the same amount of money. Maybe New York is a more expensive location, so we might give the people in New York who are assistants 15% more than the people who are assistants in Knoxville. So maybe it's that the position in a branch determines the salary. So these are all things you have to tease out, okay? Often by interviews, asking someone. Okay, but I think it should be pretty clear that the branch address here is a duplicate. You're duplicating that information, and that's leading to the possibility of redundancy. Okay, so that in fact is called an update anomaly. The fact that if I change, let's say I go in and change the branch address for John White to, or let's just say I change the branch address for B5 to be 10 Downing Street. The Prime Minister just took over. And it's, now I have to remember to update it everywhere. For every tuple that is B005, I need to update it to be 10 Downing Street. If I forget, then I have what's called an update anomaly, because now there's inconsistency. Okay? Now, there's also something more subtle that you may not be seeing, and that is, let's say that I want to create a new branch, but it's not yet got any staff in it. Maybe I'm building a new branch. We're going to call it branch B10, and it's going to be in Knoxville, Tennessee. And I want to insert it into this relation. Well, does anyone know what the key for this relation is? Remember I said it's essentially a directory of staff. Staff number should be the primary key. So I want to insert a new branch, B10, that we're building in Knoxville, Tennessee, but no staff are assigned to it. Okay? So if I try to insert such a tuple into this directory, I'm going to have nulls for the staff attributes. What does the relational model have to say about null values for primary keys? Not allowed. So I actually can't insert a branch into this directory unless there's a staff member associated with it. So that's called an insertion anomaly, because I can't actually insert information about a branch unless I also insert information about a staff member. Okay? So these insertion anomalies come about when you try to have multiple entities in the same relation. In this case, I'm in effect keeping information about both staff and branch in this directory, rather than keeping one relation for staff and one relation for branch. Okay, so basically, whenever you have a relation that is trying to keep information on more than one entity, you're going to end up with insertion anomalies, where in this case, staff is kind of like the boss entity, right? We have to have a staff person in order to insert into here. And the reason that the staff member is the boss entity is because the primary key is staff number. So it's kind of like the branch is the dependent entity here. Okay, so all dependent entities end up with the short shrift. They can't be inserted without having the primary entity. And you get the same issue in reverse with, just like you have insert anomalies, you get what are called delete anomalies. So if, notice here, the only tuple for B007 is Mary Howe. If I delete Mary Howe from this directory, I lose the information that branch B7 is at 16 Argyle Street in Aberdeen. So that's called a deletion anomaly, because I could accidentally lose information about a branch if I delete the last entry for a staff member at that branch. Again, the dependent entity, the branch, is in danger. It depends on the primary, an entry from the primary entity being there. Okay, so we went through update anomalies. That happens when you have multiple instances of the same piece of data. And when you update it, you have to make sure you update all instances of it. A delete anomaly is when you accidentally delete all information associated with an entity. And an insert anomaly is what happens when you're unable to insert something because you don't have an instance of the primary entity. Okay. So again, the way you get rid of essentially insert and delete anomalies is you ensure you have only one entity per relation. And then the way you're going to get rid of your update anomalies is those are often relationships. And sometimes those relationships are going to get moved off into a separate relation. Sometimes the update anomalies will disappear when you separate the entities into separate relations. In this case, if we simply separate the staff and the branch relations, we'll eliminate the update anomaly as well. Okay? But as an example of something that might not eliminate an update anomaly when we separate entities, let's say I really did say that a branch and a position determined a salary. Okay? Then it's really putting the branch number and the position and the salary all in the staff relation is not going to eliminate the update anomaly potential I have. There's still the potential for duplicate information there. So not all update anomalies get eliminated when I ensure that there's only one entity per relation, whereas we basically eliminate insert and delete anomalies when we separate the entities. Okay. Questions about that? So essentially, normalization is going to be about A, ensuring only one entity per relation, and 2, extracting relationships into their own relations so that we avoid update anomalies. And when we do normalization, these are the two important properties. Basically what we're doing is normalization takes a big relation and decomposes it into smaller relations. And when it does that, it needs to maintain these two properties. One is lossless-join, meaning we don't lose any information when we separate or decompose the relation. So if we separate the staff-branch relation into a staff and a branch relation, we shouldn't lose any information. We should be able to join them back together and not lose any information. And so when we do the lossless join, that's ensured through foreign keys. Foreign keys are what give us the lossless join property. And we also want to preserve any dependencies. Those are relationships. So if there was a relationship between two or more attributes in the original relation, then that relationship should be maintained in at least one of the decomposed subrelations. So for example, that if I really did have a relationship that the branch and the position determine the salary, then that relationship needs to be maintained in at least one of the two decomposed relations. So that's what dependency preservation property means. Basically, if there's a relationship among attributes, that relationship is still preserved in one of the decomposed relations. Okay, so dependency preservation, functional dependency, and relationship in the ER model are one and the same. So in the ER model, we talk about relationships. When we're doing normalization, we talk about functional dependency. So remember I said normalization is more mathematical. Okay? So we actually have, in the case of normalization, we have a mathematical definition for a relationship. We call it a functional dependency. And we say that B is functionally dependent on A if each value of A is associated with exactly one value in B. It's kind of like A is the primary key and B is the dependent part. But A in this case isn't really a primary key because the primary key uniquely identifies the entire tuple. Okay, so as an example, when I said back in the staff-branch relationship, actually let's do this way. So one of the things was basically if I say that the branch number and the position determine the salary. So that's not a primary key, right? Branch number and position is not a primary key for that staff-branch relation. But what I'm saying when I say this is a functional dependency, I say that a branch number and a position uniquely determines a salary. Okay, there's not going to be like, let's say for me, branch number is B005 and I'm a professor and I make 50,000 and Bentley is also at branch B005 and is a professor and makes 100,000. That won't happen. This, I know, you're thinking Brad needs a raise, not Bentley needs a, we'll split it. Bentley's like, you won't like it if you're making 100,000. You only like it now because you're not making that much. There's good behavioral economics that show that if someone has 5 million and loses 4 million to have $1 million, and one person has nothing and makes $1 million, now has $1 million, both you and I have $1 million. But if you lost the 4 million, you hate life. Whereas I am walking on sunshine. So that's what I'm saying. You might not be so happy to give up that 25,000 if you. There we go. You're generous. That's right. You got your big heart. Big heart. I like that. Those poverty-stricken ones. Okay. So at any rate, This is a function. All a functional dependency is saying is that the attributes on the left side uniquely determine a value on the right side. And it could be one or more attributes on the right side. Okay? It doesn't have to just be a one. But this is a relationship. It's saying that branch number and position determine salary. There's a relationship among these three attributes. Now notice this is a little different than the relationships in the ER model, because in the ER model, the relationships were always among entities, right? And now the relationships are actually more among attributes. Okay, so it is a bit different because, so we are at a more coarse-grained level here with normalization, because we're talking, our relationships are now between attributes. Before, in the ER model, the relationships were between entities. So normalization, functional dependencies describe relationships among attributes. So if you have a situation like this where the position does not determine the staff number, because you can have multiple staff associated with a position, but the staff number does effectively determine the position. You can have only one position. So for whatever reason, they call the left-hand side the determinant. So that is the independent variable. So in math, you say f of x equals y. You call x the independent variable and you call y the dependent variable. But in normalization, x is the determinant. Okay, so the left-hand side is the determinant. And the right-hand side doesn't have a name. Okay? Now, one thing you got to be careful of. Have those of you who have had Dr. Planck may have heard him refer to proof by Cosmos. So he's referring to Cosmopolitan magazine, which he doesn't particularly care for, because he felt that it spouts off lots of things they claim to be true that really aren't. But the point is, sometimes if you just look at a relation, you may think that you see a relationship that doesn't really exist. So if we look at the staff-branch relation, it really looks like we have that every name uniquely determines a staff number, right? Because there's no duplicate names. So this is proof by Cosmos, because we're just looking at a bunch of examples, and from those examples, we might infer that the staff name determines the staff number. Before you go making that assumption, you really need to check that with someone. Okay? In the real world, I guarantee you that it is rare that a name uniquely determines a number. Okay? Even as uncommon as Brad Vanderzanden is, I have found another Brad Vanderzanden that is out there. So even my name is not unique. Okay, now it's unique, I believe, within this organization, but it's not unique in mapping to a social security number. There's another Brad Vanderzanden Exton out there who maps to a different social security number. So you have to be very careful when defining functional dependencies that you verify that this is really the case. You might talk to some people in the company or whoever your customer is and make sure that that's really the case. So, and that's why it says that they have to hold for all time. It may be that at a moment in time, like here at UT, there may be currently no student on campus with a duplicate name. I doubt that, but it's possible. But in order for a functional dependency to be modeled using normalization, it has to hold for all time, not just right now. Okay, so that's important. So staff number is supposed to uniquely determine staff name. And why is that? Because they assign unique staff numbers. That's the point of a staff number. That's the point of a student ID. That's the point of a social security number. It uniquely identifies you. It holds for all time. Whereas the reverse, the staff name determining the staff number, it's not holding for all time. Okay, so you just have to be careful you don't fall into that trap. Okay, so in order to be called a functional dependency, your determinant must have the minimum number of attributes necessary to maintain it. Sound familiar? Remember, primary keys and candidate keys had to have the minimum number of attributes required to uniquely identify a tuple. So same thing, a determinant has to have the minimum number of attributes necessary to maintain the functional dependency. And that requirement is called a full functional dependency. So for example, it is true that staff number and staff name together determine the branch number. But that is not a full functional dependency because, or it's not called a functional dependency because staff number by itself uniquely determines branch number. So the determinant here doesn't have the minimum possible number of attributes because staff name is superfluous. So this is called a partial dependency. It's not called a full functional dependency. It is called a partial dependency because you can eliminate attributes from the determinant and still maintain the dependency. Okay? So this is just summing up what I said about functional dependencies. They're one-to-one. They hold for all time. Their determinant has a minimum number of attributes. Okay. The other thing we have to be on the alert for is transitive dependencies. Should be most of you are familiar. If A determines B and B determines C, then A determines C. Okay. So that's called the relationship A determines C. It's not written on the slide, but A determines C. That is called a transitive relationship. And we don't explicitly write out transitive functional dependencies in our normalization schemes. We write out A determines B and B determines C. We don't write A determines C. So you need to realize that transitive dependencies exist implicitly, but you don't explicitly write them out. Does that make sense? You write out the two parts, but you don't write out the actual transitive dependency. Okay? So this is an example we have in the staff-branch relation. The transitive dependency is that the branch number determines the branch address, which in fact, when we decompose and put the branch information into its own relation, this transitive dependency moves off into the branch relation. Okay, so here is an example. We want to identify the set of functional dependencies for the staff-branch relation. So that directory one we showed earlier, the obvious one is the staff number determines pretty much everything. The staff name, the position, the salary number, and the branch number. It also determines branch address. Okay? Why is branch address not also shown on the right-hand side? What did I say a minute ago? Transitive dependencies are not explicitly shown. So it is true that staff number determines branch address, but it's a transitive dependency. Staff number determines branch number determines branch address. So branch address is not up here on the right-hand side for staff number because branch address is transitively dependent on staff number through branch number. Therefore, we separately write out the functional dependency that branch number determines the branch address. Now, this is an assumption. I think it's a reasonable one. The branch address does uniquely determine the branch number. That's why we give streets addresses, so that they do uniquely determine things. Otherwise, the postal folks would have trouble delivering stuff. So it's actually fairly reasonable to say that a branch address also uniquely determines a branch number. And then I said that the branch number and the branch number and the position determine the salary. It's true that the branch number and the position determines the salary and that the branch address determines the branch number, then this final functional dependency must also hold. So the obvious one would be branch number, position determines salary, and staff number determining everything else. The subtle ones are branch number determining branch address determining branch number, and branch address and position determining salary. That's kind of teasing it out from the other relations. But this is pretty mathematical. You can kind of, once you've verified it with someone, it's like, yes, the branch number and the position determines the salary, and we want to enforce this in the database. Basically, functional dependencies are constraints that we want to enforce in the database. That's so important, I'm going to write it down, because I want you to also, this is important. Basically, every functional dependency is a constraint we want to enforce in the database. We also don't want this to be redundant. We don't want to keep redundant information with functional dependencies. So if somehow we would prefer not to have branch number and position, the same branch number and position, listed multiple times, because it always is the same for salary. So with functional dependencies, we kind of just want them listed once, because if they're listed twice, we have a consistency issue. We have redundant data. Okay, so functional dependencies are important because we don't want functional dependencies to really appear more than once. Okay, so once we have, basically with normalization, the first step is determining our functional dependencies. Then we're going to use the functional dependencies to decompose our relation. And the first step in that decomposition, once we have the functional dependencies, we want to identify a primary key. That's usually pretty easy. Okay, we've already talked about how the primary key should uniquely identify every tuple in the relation. So typically, there is a particular determinant that is going to determine all of the other attributes in the relation. Okay, and for the staff branch relation, it's pretty clear that the only one is staff number. Okay, nothing else is going, other than the whole tuple, is going to work. Okay, so we have now kind of the building blocks in place for normalization. We identify functional dependencies. We're going to use them now to decompose a relation into a smaller set of relations. And basically, normalization has steps. We talk about zero normal form, first normal form, second normal form, third normal form. So it's an algorithm that goes through steps to get to progressively more restricted relations that have less redundant data in them. Okay, that's the Book's diagram. We're only going to be concerned up through third normal form. These additional normal forms are left to graduate courses. And your biggest bang for your buck comes to third normal form. After that, you don't get as big a bang for your buck anymore. Okay, so we start with unnormalized normal form. That's the least restrictive. Okay, and it's a table that can contain multi-valued attributes, which doesn't even conform to the relational model, because the relational model doesn't allow multi-valued attributes. So zero normal, I call it zero normal form. Unnormalized form means you have a table, but you have multi-valued attributes. So to go from unnormalized to first normal form, you simply ensure that there is one value per cell in your table. So you're getting rid of, when you go from unnormalized form to first normal form, you're eliminating multi-valued attributes. Okay, which means that you either, with your repeating groups, which are multi-valued attributes, you either place the multi-valued attribute into a separate relation, or you create enough columns to handle that multi-valued attribute. For example, if you have telephone numbers, maybe there's a maximum of 3 telephone numbers per branch, you could create 3 columns for phone number 1, phone number 2, phone number 3. That approach is horrible. Don't use it, ever. Okay? It really complicates your queries. How do you feel about writing if telephone number equals phone number 1, or telephone number equals phone number 2, or you get the point. Your queries get to be pretty nasty. So solution 2, where you place the multiple attributes into the multi-valued attributes into a separate relation, is far better, where you just have a branch number and then the phone number. Branch number, phone number. Okay? So the relation would be, it'd be like phone number relation, and it would just have a branch number and a phone number. But now you could have 3 tuples, one B005 with one phone number, B005 the second phone number, and so on. So now it would be, once you've moved the multi-valued attributes out to their own relations, you have first normal form. Okay? Second normal form is where you remove all the partial dependencies on the primary key. And it's easiest to show an example. So here is our client. We have a client-rental relationship right now. So this is essentially a lease. Think of this as a lease. So we have client, the property number, when they started renting, when the lease finishes, what the rent is, who owns the property, and the owner name. So can you read this back there? Is it not? I'm afraid it's kind of. So you have to kind of follow along then. So we have client number and property number determines the start and end of the lease. Okay, so we're assuming that a client never rents the same property. We're going to make an assumption that the client never rents the same property twice. We're assuming that if we know the client and the property number, we know when the lease began and ended. Now we assume if we know the client number, we know the client name, and if we know the property number, we know the property address, the rent, the owner number, and the owner name. Now notice that client number and property number also determine the client name. But I didn't show it in that relationship, and the reason is it wasn't minimal. So the client number by itself determines the client name. Therefore, I didn't have an arrow here because that wasn't a minimal determinant. Same thing for property address, rent, owner number, and owner name, those are uniquely determined by the property number. In fact, the property number really shouldn't have an arrow. See how I get better with time? This arrow to owner, this arrow to owner name should not be here. And why is that? Because owner number determines it. So really, this arrow should not be here because it's a transitive dependency, and we don't explicitly show transitive dependencies. Okay, now, so that's what it turns out. Client number and property number are a primary key because together with client number and property number individually, they determine all the other attributes. Okay, so I'm just going to hold you for a couple minutes, not much more than that. So there's a couple candidate keys that you could have too. So it turns out that if you know the client number and when the rent and the beginning of the lease, that's also going to determine the property information because our assumption is each client can only rent a property once. So if we know the candidate and we know when the lease started, we know which property they rented. And similarly, if we have the property number and the rental beginning of the lease, we assume only one client is on the lease. Therefore, if we know the property number and the beginning of the lease, we know who the customer number is and we know when the lease ends. So it turns out these two functional dependencies here, these are functional dependencies, they are candidate keys because they also can determine all of the attributes in the relation. But we're going to choose the client number and the property number as the primary key. And I'll end with this thought, which is, so I said, when you go from first normal form to second normal form, you're going to remove all partial dependencies on the primary key. So what's going to happen, and we'll get into this next time, is that this relation, what we're going to do is we're going to remove this partial dependency here. We're going to put client number and client name into their own relation. And then we're going to put property number and all of its attributes into its own relation. So what we're doing is client number is a subset of the primary key, and similarly property number is a subset of the primary key, and therefore we're going to remove those two dependencies and put them into their own relations, which makes sense because if you think about it, client is an entity and property is an entity. So what we're really doing is we're removing the client information and putting it into a client entity relation, and we're removing the property entity information and putting it into a property entity. And we'll go into more detail on that on Thursday. Yes, Thursday. So don't worry, your homework for this is not yet in place. And then on Thursday, we'll go through a case study too so that you have a better idea of how you apply this in the real world. Okay, so I will see you all on Thursday.